Round of applause before we even started. Let's see what you think at the end. So thank you very much for coming back. Hopefully I can continue the great talks that we had this morning. I'm going to be talking a little bit about robotics. And in particular, I'm going to be talking a bit about the problems of how you do navigation on mobile robots. So this is a slightly different perspective from some of the software talks that we saw this morning, but it's still software related. At the heart of these robotic platforms is software. They're just embodied in these vehicles, and they are sensing the world through these very complicated sensors. So a little bit of an introduction to me first. So my name is Antony Waldock. I've been in the development of kind of robotic and autonomous vehicles for about 20 years now. Whole variety of things, land, air, and sea. And here are kind of two examples of some of the platforms and vehicles that I've worked on. So this is a autonomous vehicle that was developed to help infantry carry heavy loads. You can kind of see a mock injured person on the back there, a dummy, which was the weight of a soldier. It was significantly difficult to get on there. And this had autonomous modes to drive around on Salisbury Plain, such that, for example, the soldiers could then send it forward, collect up injured people, and bring those back to safety. And I was involved in doing these trials over a month period in February 2010 with the Army to some great success. But at the core part of this was the navigation system that allowed it to navigate using a global positioning system to go from A to B when commanded. And that was the kind of core software running on this system. Great doing trials in February. In Salisbury Plain. And this one over here is again based around navigation, but here what we're looking at is UAVs. So here it's a kind of a model aircraft UAV, so not the kind of large-scale unmanned aerial vehicles that you get in the military. Looking at seeing whether we could get it to fly more like a bird, to be able to do things like perform perch landings. And here we was looking at landing at this particular location. This was done in collaboration with Bristol University. So just south of here, we did these trials. But again, these were based on trials in February time. And so the one thing that I've kind of learned from this is, and that shared in common with both of these kind of developing these software systems and the research that went behind these, was that I ended up debugging code in February. In a field, in the cold, which is not what you want to do. And certainly in my current role at Dyson, I don't want to be debugging your robotic vacuum cleaner in your house. And so rigorous testing of these kind of robotic platforms is a must. And I'll kind of go on to talk about how we do that kind of software development through this presentation. But let's go back a little bit first. So I'm going to talk about kind of three different areas. I'm going to talk in general about the challenges in navigation in robotic platforms, and talk a bit about different types of platforms, different types of sensors to be able to do the navigation, and the different types of algorithms that can be used to do that in the software environment. And success to you all. You've all managed to arrive here. You've all managed to navigate to this location today, probably using very different strategies, I would assume. Some of you probably tried to use the GPS on your phone and found that the 4G network was down on O2, so it didn't work incredibly well this morning. Some of you probably used prior maps, like these ones, which have been floating around in Bristol for quite a while now. Some of you may have even spoke to someone and asked them directions as to how to get here. And therefore, you're kind of navigating via probably landmarks. So you've identified things like churches or the fountains just out here tend to be a good navigation aid. So I'll talk a little bit about the different platforms and how to navigate. I'll then bring it back to my current challenges in terms of domestic robotics. So how do we make domestic robotics navigate around in the world? And we'll be talking a little bit about this platform this vehicle that Dyson currently make, which is the 360i, which navigates around homes to be able to do vacuum cleaning. And then I'm going to talk a bit about future developments. I'll obviously keep this quite broad because I'm not here to announce products, and that's way above my pay grade. So we'll talk a bit about the future developments, certainly within navigation, mainly applied to domestic robotics, but you could see how we could apply it to other areas. So kind of diving straight in, I'm going to talk about 3 different areas which you've probably heard of in the media. So talk a little bit about drones and what are the tasks that a drone does and how it flies and how it navigates. A little bit about driverless cars, and you might think, oh, all that's done in the States, or it's done by a couple of companies in the UK, Oxbotica or 5AI, based here in Bristol and Edinburgh. But there are actually some other projects that are going on. So this is the Ventura project, which is just finished here in Bristol, looking at acceptance of driverless vehicles. And so I'll talk a bit more about that later as well. And then finishing off with domestic robotics and the aims and the challenges involved in that. So talking a little bit about drones first. So how many of you own one of these types of drones in the audience? Not many. Oh, one at the back. So I own one of these Mavic Pros. The whole idea of these types of platforms, the tasks that they're there to achieve, certainly these ones, is to hang a camera in the sky. It's kind of regardless about how they do that, but the task and the aim that they're trying to achieve is to allow someone to take video from a different perspective up in the air. And the way they achieve that task is to be able to say, okay, we need to put that up in the air. We need to be able to stabilize the control of that system such that reasonable novices, I class myself in that, can be able to fly these things. And to be able to do that, they use GPS. And so the global positioning satellites, which are orbiting the Earth, and they use the signals that they receive from that to be able to localize themselves. And GPS is really good for localizing where you are on the face of the Earth. As I say, we all use it in our phones. Most days, I would argue. But really, in this context, it's not used to navigate from A to B. It's predominantly used to stabilize the platform. And they can write some software and control loops, DGI in this instance, can write software control loops to be able to stabilize the platform. But if you've ever flown some of these things, you'll notice that they do drift over time. And that's because of the accuracies that you get with GPS. So GPS, in its kind of raw form, is an accuracy of plus or minus 4 meters. So that's saying if I took off from a particular location and I tried to bring that aircraft back to that location completely automatically, purely by GPS, it may be up to 4 meters off. And that's not kind of a guaranteed that it's going to be 4 meters off. It's a distribution over time. And it tends to get worse over time as well. So the flight time of these things is about 27 minutes, maybe 30, if you take a lot of the stuff off. And in that period, a lot of the errors in GPS is related to atmospheric errors. So you'll find that it will land very accurately back where it started. And it's great to be able to do these kinds of platforms. But it really breaks down when you can't see enough satellites, for example. You probably need more than 8 satellites to be able to navigate using this. So when you've got a clear sky and you're away from objects, perfect. There are some modes that they've started to integrate. So there's collision avoidance sensors on the front, which get folded into the navigation system to avoid things like trees. And also you can select modes where it fixates on a target and then follows that target. So for example, if you're doing mountain biking, you can use this to track you. But there's a number of issues if you want to use this in more kind of built-up environments. But these types of platforms are not just used for cameras on the front. We can add other instruments on it. And therefore, we can make use more of the GPS navigation systems on it. So I'm going to show you a video which was from some friends that work at Bristol University. Tom Richardson in the aerodynamics department. So they went out to Guatemala to look at sampling, gas sampling, volcanoes that are about to or are erupting. So this is completely their work. I'm kind of showing it as an example of where UAVs could be used for these completely automatic operations. In this instance, it took off automatically. It navigated to the top of the volcano automatically. There was a bit of manual beyond line of sight operation at the end to be able to get it to fly stably through the plume, but they are looking at improving that so it does it completely automatically, to be able to sense the gas within the volcano and to be able to bring those readings back to the operator. So these kind of UAVs are really good for when you're in these huge open environments. There's not really much to hit here other than this plume cloud, which they're looking to hit anyway. And so they're really good examples. Another example that you've probably all seen is around driverless cars. So I think we've all probably seen a lot in the news, and certainly Waymo have announced yesterday that they're launching a commercial operation now, which is open to the public if you live in a certain part of Phoenix. Really, you can kind of think of this as being navigation on an obstacle. So the Earth is an obstacle, and there are lots of things that you have to be able to navigate around. And a lot of this technology came from some US government-funded projects back in 2004 in relation to something called the DARPA Grand Challenge, where they set universities a challenge of saying, well, can you drive fully autonomously across a desert? And they had to drive 212 kilometers across this desert completely unaided from start to finish. And a lot of universities entered. This is Stanford's entry, Stanley. And in the first year, 2004, nobody did it. They all got about halfway, and they didn't succeed. And this was done purely by GPS. And they came back in 2005, and 5 teams managed to finish. So the task here, they're navigating from A to B. They're using a whole variety of sensors. So here they're using GPS on the back. They're using 3 GPS antennas, all fed into a system. They've got an inertial measurement unit to get them through periods where they have no GPS, because there was a few tunnels on the route. And they're using these LiDAR sensors, where you kind of, like my laser pointer, you shine it out, it gives you a return, and it tells you the distance back. And they can fuse all that together in the software to be able to determine what the road looks like in front of them, whether it's drivable, whether it turns left or right, how fast they should drive. And Stanley was the first one to complete in about 8 hours. And from that point on, they started to develop the technology, which has eventually come into the Waymo vehicles. There's been, over the years, less and less reliance on GPS as they've moved into more built-up areas. Still used kind of to initialize the start and the end. But a lot of the reliance is based on this sensor up the top here, which is a spinning version of this LiDAR sensor. I had the privilege to play around with the first one of these sensors when it was built back in 2004. And you get about 1 million points out of it a second. And it gives you these really detailed maps of the environment around you. And a lot of the navigation systems that are on these driverless vehicles are actually using these to build up a map and then compare it to a prior map, which is one of the reasons Google or Waymo only drives in certain regions, because they've already been out and mapped it in very great detail. And then what they do is they compare the map that's generated by the sensor on the top to the map that they expect to work out where they are exactly in this example, in this environment. So, for example, if the vehicle was down, I have to drive on the US side, this side. If they're on this side, no, that side, then they'd be going down towards the junction, and you'd be able to localize yourself based on these kind of central ridges and based on the kind of pavements and maybe the buildings that are starting to come up. So this is great technology, and they're out there deploying it, and they're really at the stage now where the localization and navigation system works phenomenally well, but the bit where they need to be able to do a lot more testing is around what happens when it's got other drivers in the environment, or there are parts of the environment that they don't necessarily expect to see. So maybe there are some artifacts within the map that confuses their navigation system, or maybe there are behaviors that happen which are corner cases which confuse their navigation system. And that's really where their testing is focused at the moment. They're testing in simulation, they're testing out in the real world to be able to find those corner cases. And that's particularly important when you're building software for robotic platforms. A lot of the uncertainty is inherent in the environment and in the sensor systems. And some of that testing is being done here in Bristol, up at UE. And that focus really on the Ventura program is around driverless cars acceptance. So do people accept how a driverless car operates? So are they too conservative? Do they wait too long at junctions? How do you know when it's about to pull out? All of these kind of acceptance criteria. Is the ride smooth? And that's some of the knowledge that Waymo are trying to elicit as well, but they're obviously not publishing that because that's going to be part of their secret sauce going forward. So that's kind of driverless cars, and the navigation system's very much reliant on these LiDAR systems. So there's a whole bunch of testing around how other people operate around a driverless car and how they operate. But how do these LiDAR systems work in different environments? So a lot of the testing that driverless vehicles have been doing are in nice sunny climates. And I've taken one of these Velodyne sensors out onto Salisbury Plain in foggy weather, and they don't work particularly well because they bounce off things like rain, and they also bounce off things like snow. An example of that was shown by Google earlier this year. So this is a slide that I took from the Google keynote. So they're testing out in Detroit. And you can see the actual scene here. It's very difficult to tell how snowy it actually is. Maybe in Bristol weather that looks foggy to me, but there's definitely lots of snow on the ground. Number of cars are in the environment. And this is the return that you get from the Velodyne sensor, or the sensor that they have mounted, which is a slightly different one. So that all these kind of pink blobs are classified as objects, i.e. their height off the ground. And you can kind of see it wouldn't really move anywhere. It would kind of think, oh my God, I'm surrounded by loads of obstacles. I'm not going anywhere. And the remarkable thing that Google have done, or they announced certainly at this keynote, was they said, okay, well, we've used machine learning. They didn't explain what that was. They've used machine learning to be able to filter out these anomalous readings that are returned by snow. And here you can see they've written bounding boxes around the cars that are in the image. And I can't actually see that one over there, so I'm not entirely sure. It must be off the frame, I guess. But the kind of question that I have after that was, okay, maybe they've filtered out all of these measurements, but if they're using that point cloud for navigation, they've now got a lot less points to be able to compare to their prior map. So how does it affect how accurately they can navigate? And I'm guessing that's what they're learning at the moment. How well they can do it in different environments, in different climates. So there are a number of different approaches. There are, for example, 5AI are using very much a machine learning, a machine vision approach to this. So they'll have slightly different failure cases, but it might allow them to navigate in things like snow and rain. So it'd be interesting to see how they progress over the next few years. So now we turn our attention to domestic robotics, the one that is my kind of challenge at the moment. And I would say it's the hardest environment to navigate in. So this is a typical environment. This is my house, so I'm allowed to use this picture. And this is my son's room. He's actually quite neat, so he wasn't very happy when I messed his room up for this picture. But but there's lots of nice things here, and certainly with domestic robotics, if you're developing a vacuum cleaner, we now want to navigate very close to obstacles because we want to cover the entire floor. And we now want to be able to do complete coverage of this as well. So we have to navigate next to those obstacles. And there's lots of very difficult obstacles like deformable objects, like teddy bears and bits of paper. There's also different kinds of floor surfaces. And also, there's no way I'm going to get a prior map of your house either. So there's no way I'm going to be able to do that. And also, unlike driverless cars, which are very much seem to be operated as a service, this is a product you buy, you take it home, and we don't see it again, hopefully. And there's also other dynamic obstacles here. So a colleague of mine's children, and they're having fun dancing in front of the robot. So anything could happen to these systems. So you're putting it in an environment where it's quite difficult to navigate. So how do we do navigation? We don't have a prior map. We can't get GPS. And so what we have to do, we have to turn our attention to finding our own satellites, basically, or finding our own landmarks if we're talking about navigation via things like churches and buildings and houses and things. So I've tried to remove most of the maths around this. But the idea is that you kind of start off at a particular location. You know where you start. And this is a relative map. So you don't know where you are on the face of the Earth, but you know where you are in relation to the start condition. So you start off, and you identify some features in the environment. In our particular case, we use a camera to be able to identify those features. And those features could be just very high contrast bits of the image, and you'll see that later. We then move, and we have an idea of how we move. We then try and find those features again that we saw previously. A bit like our satellite system, we try and associate those features that we identified with features that we've previously seen. And then we try and work out, well, has the feature moved or have we moved? And how have we moved in relation to the feature? And we can do that lots and lots of times, and eventually we converge to an answer of saying, well, we know how we're moving, and we know how the features are moving around us. And we tend to call these things landmarks that we find in the environment, and then we are navigating in relation to those landmarks to be able to achieve coverage patterns like this. So a better way to kind of describe that is to actually see it in action. So again, my son's room, and you can just about see the robot down the bottom here. The first thing I always have to say is this is a development rig. The ones in production that you would buy and take home with you, you cannot get this data out of. The hardware does not exist for you to be able to get this out of for Data Protection Act, data protection. So I can do this because I've got a development rig that has special hardware attached to it. So here is what the robot is seeing from its panoramic camera. And these green circles that you can see and the patches within them are the features that it's identifying. So you can kind of see that the features that it's finding are not really human representations of features. They're just very good high contrast patches. And this is called monocular SLAM, simultaneous localization and mapping. And this kind of shows what it thinks it's doing. The blue path is what it's planning to do. The green path is the path that it actually executed. And you'll see some deviations from the path every now and again. Due to things like slippage on the floor, or maybe as it fell off the small dip in the rug, it kind of moves, and therefore it's not navigating exactly the same as what you would find. And then these kind of white dots that you might be able to see appear every now and again with the lines coming through are because we have no estimate of depth. Because we're using a single camera, if I look through a camera, I know an object is at that bearing. I don't know where it is. But then if I move and I see it again, I know through triangulation where those features are. And here it is doing a standard clean, and it's navigating around, following that, identifying obstacles as it navigates around. So that's the kind of SLAM system that we have on board that will be able to navigate in every home across the world is our aim. So obviously, vision is not going to be enough. There are failure cases for any sensor that you can put on. In this example at the top here, someone's accidentally dropped something on the camera, so you can't see. In this example, this is an example that we recreated from feedback from a customer of saying, what happens if you put bunny ears on the robot? Because typically kids love to give these things names and talk to them. And so one failure case would be, OK, let's put bunny ears on it and see how it behaves. And actually, it navigates really well with these bunny ears on. So obviously, we can't pick up features in these spaces, but it learns to ignore these because they don't behave as the robot expects it to behave, and it focuses on features in the background. But vision is not enough. So we need other sensors on board. And in particular, we need sensors that are telling us how we're moving, where we are in the room, and where are the obstacles. So I'm not going to go through this as a kind of exhaustive list, because I'll eventually run out of time and I want to cover some more stuff. But we have things like inertial measurements to tell us the forces on the robot, gravity being one of those forces, wheel encoders to tell us how the wheels are moving, and then we have things like where are the walls, where are the obstacles, and have we hit anything. And we can use all that information, fuse it all together in our big bit of software to be able to determine how we can get from A to B, or how we can do a coverage pattern. To be able to efficiently clean your house. And that's particularly important because the vacuum that we have in here, the cyclone, takes a lot of power because we want to pick things up properly. And so we want to go over an area once and once only, and we need to be able to navigate efficiently to be able to do that. So just out of a bit of interest, and I thought maybe at this time after lunch we might be flagging a bit, so just to have get in perspective of the kinds of testing that are required to be able to achieve this level of software. So these are driverless vehicle tests. These are the miles driven up to November 2017 in California. So in California, they have strict regulations that if you test your vehicles there, you must tell them how many miles you've done and over the time period that you've been trialing them in California. So this is not kind of representative, I guess, because like Google announced, or Waymo announced recently that they've done 5 million miles. So they are way ahead of most people. But it gives us an indication of where driverless cars are in the testing regime. And then just for a bit of fun, we get analytics back from our platforms at a very high level, but they tell us things like how long they've been cleaning, for example. And so I thought, well, where are we if we were a driverless car? So with our fleet of autonomous vehicles, which are navigating around, we come second in the list with 176,000 miles we've covered. And it's a bit different because we're a product. We're not testing in people's homes. So you could argue these are a bit maybe apples and pears. But we are kind of second in that list if we were in California. Now, we're obviously ridiculously small compared to a driverless vehicle. So if we scaled it up to actually driverless vehicles, then we would be in the lead in California. But anyway, I thought that was quite interesting just to see where we are in relation to autonomous vehicles and the deployment of autonomous vehicles. So one of the mantras that we had, going back to my original statement of I do not want to be debugging the vacuum cleaner in your house or on Salisbury Plain in February, how do we prevent doing that? And it's really around testing. We want to make sure that we're delivering the best product. And we can do that at a whole variety of different levels. So we do it before we even start designing the code, we do algorithmic testing. And the algorithms team are very hot on design and testing of those, prototyping them, actually on real platforms before we even do any integration into the software. We integrate them into the software, do unit testing, regression testing, and then run thousands of miles in the simulator to make sure that any of those changes are not going to have adverse conditions. We then do lab testing. So we are very lucky in the fact that we have great facilities, both here in Bristol and up at Malmesbury. We can be able to test these things in relatively realistic environments in the lab. And then we do a lot of home trials. So we have both developers who take developer rigs home, and we also have employees as well that sign up to our scheme and take these rigs home. And there we get full logging where people approve of that. We then can test those, and a good example is we've got the next generation of product, not the 360i, but the Dyson Hurist, which is available in China at the moment. Before we even got to beta trials, just in those home developer trials, we drove from here to London. We did 145 miles worth of testing just in that element alone. So, and that's not counting all of this lab testing and regression testing in the simulator. We then do beta testing, so we go into people's homes. There we don't have full logging. That is purely for analytics and to give an opportunity for them to give us subjective feedback. And then we get analytics from customers, again, high level, anonymized, and we have the opportunity to do over-the-air updates as well. So a little bit about, well, where's this field going next? So in the SLAM system, identifying features, you noticed that those features were not really human representations. They are high contrast patches, for example. And we want to say, well, where is the next generation? And this is an example. So this is taken from Imperial College. So Dyson have a lab there where we sponsor some work around navigation by one of the leaders in the field, Andrew Davison. So this is his work and his colleagues' work who were displayed at the beginning there. And here, what they're doing is taking advantage of machine learning. So machine learning's come on in rapid evolutions over the last few years. So here we've got a kind of normal camera image, red, green, blue. We've got a depth image, which can generate it, so very much the same as your Connect, generating a depth image. And we can combine those two together to get these kind of colored point clouds. And in those colored point clouds, we can identify objects from their shape or from what they look like. And these objects, we can then localize ourselves in relation to those objects. And you might ask yourself the question, well, why do we want to do that? Those objects might move. So a chair, maybe someone's going to come in and move that chair. It's much more robust to be able to different lighting conditions, for example. So those patches that I showed you earlier, then they do suffer from things like if people turn the lights on, for example, or if the sunlight changes radically, the contrast will change in those. Those images, you're picking out larger features. You're picking out larger features which are more robust. They're more likely to be there. That fridge, for example, at the beginning is very unlikely to move. If it does move, you've still got other features which you can reject that correspond. So that's kind of an idea of where this community is going. And there's a whole other thing, and there's a whole other variety, certainly within the machine learning community, where these could be used. So, for example, I showed you the depth image. There are some great bits of work about at the moment where you can generate a depth image purely from an RGB image. So that could be fused together. And this has an impact both in domestic robotics, so in this kind of example, but also in things like UAVs as well. So you can imagine a UAV using this type of system to navigate around an urban environment, for example. And really, that kind of comes to a combination of saying, well, this is a really exciting area, certainly at the moment in terms of navigation for these systems and developing the software for these. Because you've got these great advances in machine learning, great advances in the computation used to do simultaneous localization and mapping, which is the formal word for the navigation I showed you. And also coming on stream are very much low-powered hardware. So you should be able to do this all on a chip in the coming years. And that really opens up the view of saying, for mobile robotics, what can we do with this? Where can we go, both for driverless vehicles, UAVs, and in the domestic environment as well. And a little bit of a plug, we do have a stand. We are recruiting at the moment for good candidates, so come and have a chat with me. But I think at this point, I'll thank you for your attention and open to any questions.
Right, that was absolutely fascinating. So yeah, let's open up for questions. Since I have this, I have the privilege of the first one. Certainly in our house, there would be Lego all over the floor.
Yeah.
How does the vacuum cleaner avoid hoovering things up that are actually valuable?
So at the moment, the process is that if you leave stuff on the floor, it's fair game for the vacuum cleaner. It will pick up small enough objects. Large objects like Lego will probably get stuck, so it won't pick it up. But if you do happen to pick up something like a diamond ring, that's the great advantage of having a transparent bin. You know, you can see it, you can collect it out. So don't leave Lego on the floor.
So for the current vac that people can buy, why does it use a single panoramic camera over, you know, kind of a binocular vision or a radar or something else?
So always when you're developing these types of products, there's a balance between the type of sensor that you could use, its kind of failure cases, and how much it costs, pretty much. So we could augment it with a whole bunch of different other sensing modalities, like a laser rangefinder, for example, and some other robotic vacuum cleaners have those. But they're very much limited to a single plane, for example. So you'll only get it in one dimension. And the cost of them, they are prohibitively expensive at the moment. So it would up the cost of the vacuum cleaner.
I'm just interested purely in the field of navigation. Roughly, how many patents have you generated?
Oh, blimey. Quite a lot, I would have thought.
I just wonder, hundreds, thousands?
I don't know. I must admit I don't have that number, but I know certainly for the area of navigation, there's quite a lot of patents stretching back, 30 years to when this area first started. And certainly things like inertial navigation. There are ways of doing inertial navigation using both an IMU and a camera, for example, which are very well patented. So you have to be quite careful what you use.
This is really returning to the earlier question about different sensors. Are you seeing the cost of any particular sensors falling fast enough that you think they'll make a difference, not necessarily to you, but to other people? So, for example, I'm aware that the current iPhone has what amounts to Kinect looking at my face. And I'd have thought the cost point for that must have moved dramatically. Yeah,
certainly for all of the sensors, the cost typically goes down over time. So, for example, the Velodyne sensor that I talked about at the beginning, when it first came out, it was like £70,000. Google have redesigned it, redeveloped it. I think their average is about 4K now, £4,000. So that's a significant decrease in 3 or 4 years. So yeah, these things are going to get cheaper and cheaper and cheaper. So and certainly when you start to add things like stereo cameras on, they are getting cheaper as well. So yeah, we will only see these kinds of things reduce in cost to a certain price point. But when you start to match that together with the processing that's required as well, that's getting cheaper. So that's really where it opens up this opportunity to do this type of mobile robot navigation.
So you've just mentioned about companies improving the sensors. Is there a sort of consortium of interested parties in the navigation field, or is it all man, dog-eat-dog type stuff?
There used to be, certainly for LiDAR, the people ahead were Velodyne, who used to make CD players, but then they decided at the beginning of the DARPA Grand Challenge to start making these, as they were very good at pointing lasers at things. And they were miles ahead in the field. But then companies like Google or Waymo and people like Uber have started doing their own in-house designs for these things. And certainly when one of the Waymo executives left and joined Uber, that was where the big court case happened around the design of those LiDAR sensors. So I think a lot of these sensors, certainly for driverless cars, are being taken in-house. For the other manufacturers like Ford, etc., they'll probably end up buying through a single tier 2 supplier. So they'll probably converge at some point, I would argue. But I know little about that. So. Oh, one right at the back.
Hello, thank you for your talk. Do you know if there is any research effort going on towards sharing maps between different machines working in the same space, same environment?
Yeah, there's plenty of work done at universities about sharing maps. There was a talk recently I saw at CVPR about sharing maps. And there's certainly one that you can go and download from GitHub called MapLab, which is brilliant. So worth a try if you've got some spare time.
Anybody else got a question?
Right in the corner over there for you.
What's going to happen about the tyranny of the pedestrian? As in this idea that as a cyclist or a pedestrian, you can just go right in front of a driverless car and it will be compelled to give way to you?
I think that's a really interesting question. That's one thing I mention all the time about driverless vehicles. And I think there's still a large question mark about how they're going to be introduced. I would say how, because I think they are going to be introduced, but how and when is, I think, still an open question for me. You could imagine in a shared space like Bristol City Centre, if people become very familiar with driverless cars and they're compelled to stop, it could just even make congestion worse in Bristol City Centre, which I claim is very difficult to do. But so you could imagine just walking straight out in the cross and think, right, these driverless cars, they're going to stop. So I think understanding how people respond to driverless cars, like the work that they've been doing at Ventura up at the University of the West of England, is really important before we start introducing them. It's a bit different in the US because they're segregated spaces. You're not allowed to jaywalk. But certainly in the UK, it's going to be really interesting the results that they get from some of the tests they're going to be running in London. So like Oxbotica are running some tests in London. I think 5AI have said they are as well. So it's definitely a watching brief, I think. I'm not sure I will be walking out in front of them just yet, but.
I think we've probably got time for one more, if there's anybody who'd like to ask one more question.
Wait, I'd just like to ask when driverless cars and driverless taxis, I think you mentioned that Waymo just the other day announced a trial in Phoenix of actually not just a driverless car, but a driverless autonomous taxi service. When do you think we're actually going to start seeing that?
It's a difficult. I think there are two camps at the moment. There are people that are pushing that we will see it in 2021, and there are other people that believe it's 10 years away. I think we'll probably see some version of it in a reasonably confined environment within 2020. I think there's enough kind of momentum to be able to achieve that. Whether it actually gets rolled out to entire countries, I very much doubt. And whether that gets rolled out to be able to completely different environments For example, coping with things like Bristol weather, I think is a real challenge still as well. But it's all around that testing aspect of it. Although Waymo have done some pure driverless tests, they still have safety drivers in there the majority of the time because they are testing. And whether we get to that level of confidence, I think will depend on the different operating environments. So are they comfortable? And also the legal ramifications of that as well. It's a difficult question, and I think to give you an answer, I think probably there will be some confined areas by 2021, but full rollout will definitely not be for 10 years everywhere.
That's great. Thank you very much.